Finally, guys, we have come to the end of the complete lessons on separation techniques. And I want to believe that you have enough tools in your hands to feel like young scientists. But this video is designed in such a way to test just that. I want to test your knowledge of the separation techniques you have learned so far in all of our videos, from sieving, filtration, to chromatography. So if you are here, this is the first video you're seeing, you better go back and see all those videos, because we want to start right away rolling out exam-style questions. So we want to test your knowledge. This is Dr. Jan Knows Chemistry, and welcome to my platform. All right, the first question will go just like this. Why are those separation techniques important to chemists? If you can ask that, you have to pause the video, then you answer it before I supply the answers. That is going to be what we're going to do throughout this particular video. So, why are the separation techniques so important to chemists? That's the first question. All right, to answer that, separation techniques, like I've said in all the videos, very, very, very important. And that's why we have so many of them. And we have to treat them in like 3 video sessions, okay? So apart from the fact that many industries use it, the basic thing why it's so important is that chemists believe that most of the substances that we use today, they are used in pure form. You will notice that most of the substances you have where you are, you will find out that they are in form of mixtures, and we have to separate them into their respective components. And that's the reason why separation techniques are very, very important. Because when a substance is in its pure form, that we can find application for it, that we can actually use it for a lot of things. So most of the time, when they are present in the matrix of the mixtures, they are not that useful. They are mostly useful when they are in the pure form. And it's the separation techniques that will help us to treat that. And I want to believe that is actually clear for you. So let's look at the second question, so we can pick this one after the other. Remember, once I ask the question, then you answer me. Okay, so the next question is, what properties of constituents make the following separation techniques possible? All right, what properties of constituents make the following separation techniques possible? The first one here, I want to list them, is filtration. Okay, filtration. B, separating funnel. All right, separating funnel. C, we have sieving. And D, we have magnetic separation. And E, we have distillation. Okay, so the question is, what properties of constituents make the following separation techniques possible? What properties of the constituent will make this separation technique to be possible? Like I've told you during one of the lessons, I said, before you pick a particular separation technique, you must know the property of the constituent of the mixture, because that is actually what you're going to use to be able to separate it and for you to choose your separation technique. So these are separation techniques proper. But the property that makes us to choose filtration is solubility. All right, solubility. Do you know the reason for this? If you have a particular substance, let's say inside water, and it does not dissolve, because it does not dissolve, then you can choose filtration, like, okay, I can filter out the insoluble substance. So solubility is a factor or a property of a constituent of this mixture that will make us to choose filtration as a separation technique. I hope you understand that. The question is basically telling us what properties of this constituent of this mixture will make you to choose filtration. That is it. So the second one is separating funnel. All right, separating funnel. Just like I told you in one of the videos as well, when we're treating separating funnel, I think liquid-liquid mixture. I told you that for you to choose separating funnel, you must have mixture of liquids, 2 or more liquids that are immiscible. So we may be talking about miscibility here. Okay, so sometimes density plays a part. Okay, so because the lighter one stays up while the denser one stays down. But the fact that will make you to choose separating funnel is basically miscibility. Those liquids must be immiscible, just like we are separating kerosene. Okay, kerosene and water. Okay, if you mix these two, they will not form a single liquid. They are immiscible. So because they are immiscible, you pour them into separating funnel, allow them to settle, then tap them off differently. And that's why miscibility plays a very important role when we are choosing funnel. What about sieving? At the beginning of the video, I even think this is the first separation technique that we treated when I was talking about separation of solid-solid particles, all right? Solid-solid mixture. That means mixture containing only solid particles. I mentioned the first separation techniques are sieving. And I said sieving is used to separate solid particles of different sizes where a sieve will be used. So that is the particle size. Okay, particle size is the option here. Let me circle the answer for this. All right, miscibility and particle size. Can you see that? So particle size is what will give us the ability to choose sieving. When you mix 2 solids together and they are different sizes, what you do, you simply put it in a sieve. All right? When you have a sieve looks like just like your net or a particular mesh size, right? So once you put your mixture there, the smaller particles will pass through this, leaving behind the bigger ones. So if they have the same sizes, they either come together or they stay together. So there will be no separation. But in this case, particle size will make you to choose sieving because the relative sizes and the size of the sieve that you have chosen will cause that. So if you want more information on this, go and watch the previous videos we made on this separation technique. So let's go to the fourth one. The fourth one is magnetic separation. What property of the constituent of this mixture will make you to choose magnetic separation? Of course, the answer is right here. So the answer is ability to be attracted to a magnet. Ability to be attracted to a magnet. That's the answer for that. That is what will make you to choose magnetic separation. Ability to be attracted to a magnet. If this is not, if a substance or a constituent does not get attracted to a magnet, then there will not be need for magnetic separation, because if you bring a magnet close to the mixture, you're not going to get any separation. It's only if a constituent is able to be attracted to a magnet that I can talk about separation. Look at granulated iron or powdery iron or iron filings. So you mix it with sulfur. By the time you bring magnet close, the ions will be attracted, irrespective of the form, whether in powdery form, in granular form, they will be attracted to a magnet because they are magnetic materials. So it's going to leave behind the non-magnetic property substance, such as sulfur or even sand particles. So ability to be attracted to a magnet will give you the opportunity to be able to separate this. So let's go to distillation. Remember, we are not talking about distillation as a separation technique. We are talking about what property of the constituent will make this separation to be possible. Now, for you to carry out distillation, remember we distill, all right? We distill a liquid. Look at this. In a round bottom flask, let's say we have that. We distill, that means heat is supplied here. So then the liquid will start boiling before it can be converted to a vapor, and the vapor will be cooled by Libby condenser. So before this separation is possible, boiling of liquid will have to take place. And when boiling takes place, the liquid will be converted to vapor. That vapor is what we cool, and that is what we call distillation. It's just like steam coming out from your kettle. That steam is cooled by a Libby condenser, and what you have is a distillate, because we say you have distilled the liquid, and you have a pure form right there. As long as the impurity is not also volatile, that will go along with the distillate. So that is what distillation. So what do you think will be the property of the constituent that will make you to separate it? The answer is boiling point. All right, so these are exam style questions, and I want to believe that you're able to answer all these questions correctly. All right, you may let me know how you perform in the comment section. Let me see if you're able to get most of the things I'm saying. Remember, I read the question out, then you pause the video, then you answer the questions, and after you watch my explanation and you see whether you're doing well. So let's go to question 3, and let's see exactly what it says. They say, which of the 3 classifications of matter is a pure substance? Which of the 3 classifications of matter is a pure substance? All right, which of the 3 classifications of matter? That's question 3. All right, which of the 3 classifications of matter is a pure substance? Remember, let's say they give elements there, compound and mixture. All right, and mixture. All right, specifically, remember that solid, liquid, gas. We also say in the chemistry perspective, element, compound, and mixtures. More specific as a classification of matter. So which of these is a pure substance? Look at this, an element. Majority will say, wow, this is pure. You're right. If you say an element is pure, just a single substance, and nothing else is there. So now compound, if I want to define it, a compound is a substance that contains 2 or more elements that are chemically combined. Example of compound can be CuSO4, that is copper 2 tetraoxide 6. Look at this blue substance here. Very beautiful blue substance. Let me just show you. Let me take some quantity into this beaker, so you can see that. So that is a copper sulfate. That is CuSO4. Water is another compound. All right, water is another compound. Let's see, H2O. All right, a compound is a substance that contains 2 or more elements. Look at this. How many elements do you have here? How many? 1, 2, 3. So 3. How many we have here? Only hydrogen and oxygen. 2. So a compound is a substance that contains 2 or more elements that are chemically combined. Because it contains 2 or more elements, most people think we can't say it's a pure substance, but compound is also a pure substance. All right? This classification, this is also pure. So mixture is the only one that is impure. Why is that? Because it could be anything. I can mix an element with sulfur and put them in contact with water. So this is a mixture. It can be anything. A mixture is impure, and that's why we are carrying out separation techniques generally to separate them into their respective substances. A pure substance. Compound is a pure substance. Look at this. Look at how beautiful it is. It's a single component. Like this is like me as an individual. So it's the compound. Although it is made of copper, sulfur, and oxygen. But the elements there, they have been homogenized. And that's what makes them like single entity. So this behaves like copper sulfate, not as copper, not as sulfur, not as oxygen, or their combined effects. No, this simply behaves like copper sulfate. And look at the way it looks. By the time you look at it, just see that it's a very beautiful, pure substance. Can you see that? Pure. And nothing is mixed with it. So you are not seeing copper separately, and sulfur separately, and oxygen separately. All right? So copper is like maybe red, then sulfur, yellow, oxygen is colorless gas. So, but look at what you're seeing. So it has become another entity entirely. So elements are pure substances. Compounds are pure substances. It's only the mixture that are impure substance. I want to believe that you got that too. But you have to understand why mixture is impure, because it can contain as many things as possible, not in any ratio. All right. So the next question, question 4. How can we use the following to ascertain the purity of substances? So that is boiling point. That's the first thing. That is A. B, melting point. Can you see that? And C, number of spots on paper chromatogram. Let me put it like that. Paper chromatogram. All right. So how do we use these properties to ascertain the purity of substance? All right. Before you say a substance is pure, there are some criteria. All right. One of them is this, this, or this. So how do you know a boiling point? For example, if you bring this container and you tell me that it's pure ethanol, all right, so I'll just smile. Are you sure? Let's say I put it in a beaker. So you say it's pure ethanol. Okay. So if you say this is pure ethanol, fine. What I will do to test it, I'll just dip a thermometer and set up something that has to do with boiling. Okay, I will heat it up here. All right. So once the liquid starts boiling, I will check the temperature. How do you know it's going to be boiling? Then you see vapor coming out. So check that temperature. At boiling or melting, at any change of state, temperature remains constant. If it is a pure ethanol, we know that pure ethanol boils at 78 degrees. So once we check and the liquid starts boiling at that 78 degrees C, and it stays there as long as ethanol remains, they can say, wow, this is a pure ethanol, C2H5OH. All right, you can say this is a pure ethanol. Now, what about if it is not pure? You will see that the melting point will not be sharp. That's the word we use. We use the word sharp boiling point, sharp melting point. So sharp, all right, that means, sharp means that it occurs just at a single temperature. The liquid starts boiling, you check the temperature is 78, and it stays on that 78 till you boil up all the ethanol. So that is what we call a pure substance. So boiling point can give us an idea that a substance is pure, because we already know the boiling point of the substances, all right, of pure substances. So if the temperature now drags, we talk about the fact that it's in range. All right, let's say when you are boiling this ethanol and it starts boiling at 75 degrees C, then you see again that the temperature is changing. Can you see that? So 75 to 82 is still boiling. It shows that it has been mixed with another substance. That's what it means. Because the boiling point is supposed to stay there. Let me just give you an idea of what I mean. All right, if you mix ethanol and mix ethanol, which is 78 degrees, and with benzene, that is 80 degrees C. When you mix the two, you will see that you will not get the sharp boiling point, because from 78, this one will start boiling. Then 80, this one will start boiling. So it overlaps. And you just see the solution or the mixture boiling, not knowing that it has another substance in there. So how you will know when a boiling point is sharp? And what do I mean by that? It stays at that particular temperature till you vaporize all the liquid. So that is a sharp boiling point. So, but if it's in form of any range, it shows that it is an impure substance. If a question comes to you like, a particular liquid boils from 80 to 85. So what can you say about that particular liquid? He said the answer is liquid is impure. That is what we are going to mark. We're not going to mark the whole epistle, because students can start saying, oh, because it started boiling from 80, it shows that one particular compound there 82. No. The answer is, it just shows it's impure whenever it's in range like this. But when a boiling point is sharp, just a single temperature, and it stays on that temperature till you have all the liquid converted to vapor. That is a sharp boiling point. So that is what we mean by how we can ascertain the purity of substance using the boiling point. We can do that by testing the boiling point. If it is sharp, then we will know that the liquid is pure. If it drags or is in form of range from 80 to 85, 60 to 68, that kind of range, any form of range values, that shows that it's impure. So the same thing with melting point. But the only difference between boiling point and melting point is, a solid, when we talk about boiling point, is a liquid boiling into gas, all right? So when we're talking about melting, is the solid melting into liquid, all right? So this is a particular criterion to show that a solid is pure, while this one is to show a liquid is pure, all right? So melting point is a property of a solid stuff. So every solid substance too has a particular temperature at which it melts. Look at ice melts at 0 degrees Celsius. Okay, if you're melting ice, the temperature should stay at 0 degrees Celsius. If the ice is melting and you are seeing 0, then it changes to 1. It shows that that solid has incorporated another solid inside it. So that's what it is. Look at sodium chloride. As simple as it is, the common salt that you know, it melts at exactly 801 degrees Celsius. If it melts at a higher temperature or lower temperature, it may mean that the solid is not pure. Another solid is mixed with it, like calcium chloride now, when you mix it with this, because most salt comes with impurity like calcium chloride. So you can see that the melting point will no longer be sharp. That's what we are saying. So a sharp boiling point and a sharp melting point, they simply show those substances are pure. How that is direct, and that's very simple. Sharp means single temperature system. All right. So when it drags, that is when it's in form of range, and then you can say that particular substance is not pure. Now, number of spots on paper chromatogram. This is very interesting. The last topic we treated was chromatography. All right, and chromatography is very interesting. Imagine teaching chromatography for close to 1 hour, 30 minutes. So you may need to go back and learn a lot of things from it. If you are a student trying to understand the concept of chromatography, go, you will see the video, you have your needs met. Even if you are a researcher trying to isolate all those medicinal components of medicinal plants, all those secondary metabolites from plants, go over there, you will see it. Or if you are a synthetic chemist, you have synthesized some compounds and you want to purify it, go to that video and see how you can work around the formulations of how to set up the column and stuff like that. Then you would be glad you did. All right, so let's go back to this. Number of spots on paper chromatogram. Chromatographic paper and paper chromatogram are actually different. All right, so the difference is when you start a chromatography, you have a paper which is adsorbent, which is the stationary phase. That is paper chromatography. After you have carried out separation, when you have spotted your mixture here and they have separated, all right, so it becomes a chromatogram. Now, number of spots can make you to know that a substance is what? Is pure. How? If you spot something that you thought is a mixture here, and after separating with solvent, and you find out there is just one dot there. So it could mean that here a substance, because it has only one spot, that means it's a pure substance. But in advanced chemistry, a particular spot can be, we are using a mobile phase. Let's say this is methanol. We have seen cases where two substances in a mixture will travel the same way under these conditions at the same spot. And you would think it's just one spot, but there are two different substances on that spot. So you now run it in another solvent system, all right? So, and you find out whether it's still going to give the same spot. So if you do that several times, you find out that it's always one spot. So it shows that with different solvent system, that's what I'm saying, then you can see that, oh, this particular substance is pure. It contains only one substance. And that's what we're saying. So for just WAEC, NECO and JAMB, which is basic understanding of paper chromatography, how will you know a substance is pure? When it shows only one spot on paper chromatography, we say that it's pure. If they want to test your knowledge further, or let's say for advanced chemistry, for the fact that it shows a single spot on this solvent system does not mean that it is actually pure. We may probe further by testing with another solvent system, or even viewing it under UV light to see whether we have a particular UV sensitive substance, which is going to be here, all right, that you can't see with your naked eye. So you see it at a particular frequency or wavelength in under UV. So that is for that. But the point is, for your regular exam, when it shows one spot, it may mean that it is pure. So you can see how we can answer all these questions. Why is crystallization? That's question 5. Crystallization. Why is it preferred over evaporation to dryness? Okay. That's the question. Why is crystallization? Why is it preferred over evaporation to dryness by when we consider pharmaceutical companies? All right. Most of these pharmaceutical products, they are chemicals. All right. We use them as drugs, medications for different diseases, which is going into your system. So we may think that it has to be of highest purity. So the purity level must be very high if we are actually going to consume it as drugs. So crystallization gives us that opportunity. Imagine you evaporate something to dryness. Let's say it has impurity. All the water will go, then the impurity will stay with this. Just like I dissolve copper sulfate in water with some other thing, let's say salt, and evaporate it to dryness, I will have copper sulfate and that substance here. So evaporation to dryness does not mean that, it doesn't give us that pure substance that we'll consider pure enough to be taken in as drugs. So crystallization gives us the opportunity. And apart from that, most of these pharmaceutical products, some of them are, we call them heat labile. Okay, heat labile. All right. So what do you mean by that? It means those substances that can easily be destroyed by heat. All right. That shows that they change their function. Imagine some chemicals, they react to change in temperature so fast. That means temperature, especially those ones that maybe in terms of proteins and all that. We know that proteins, temperature denatures protein. Just like what drug can I think of now? Look at insulin, for example. Okay, insulin is temperature sensitive. So a temperature will denature the functions, and most of the functions of these substances, they are related to the biological structure. And once that one is denatured, it shows that the intended purpose or property that want to use them for will also be thwarted. So that is actually what we're saying. So heat labile substances, they are substances that can easily be destroyed by heat. All right. So remember that when we are carrying out crystallization, we don't evaporate to dryness. Evaporation to dryness involves prolonged heating to the point that all the water or the solvent will be driven off completely, and we have dry substance. So that one can destroy most of all these pharmaceutical substances. But crystallization, we don't wait till everything dries up. While we still have solvent, then we allow it to cool, and then we crystallize out. So number one, it gives a purer product, and at the same time, it also sustains the structure, as some of the substances may be destroyed by heat. Question 6. Which of the following the listed separation techniques? Number 1 is filtration. Okay. The next one, sieving. Okay, then separating funnel. All right, centrifugation. Centrifugation. All right, I want to use different colors. Evaporation to dryness. Evaporation to dryness. Evaporation to dryness. Can you see that? What is the other one? Distillation. Distillation and crystallization. Distillation and crystallization. All right, we have 1, 2, 3, 4, 5, 6, 7. The interesting thing is we have discussed all this in previous videos. So the question says, which of the listed separation techniques requires the use of heat? All right, so which of them? Before we can carry out separation, we have to apply heat. Okay, so you can answer the question now before I will tick. I won't let tick it. All right, I will tick the correct answer. Remember, which of them we have to apply heat before we can actually carry out the separation. All right, let's look at filtration. Filtration involves filtering out the insoluble substance. Just like you have sand particles in water, you filter it. This one does not require any heat. All right, so it does not. What is sieving? Sieving is separation of solid particles based on what? Their particle sizes. So, of course, we just use a sieve. Then the smaller particles will pass through the sieve while the bigger ones stay on top of the sieve. So, nothing really happens. So, it's just the, no, I'm talking about heat is not involved. What about separating funnel? Separating funnel is used to separate liquids that are immiscible. 2 or more immiscible liquids: kerosene and water, oil and water, hexane and water. All right, so we are trying to separate 2 immiscible liquids. So separating funnel is better for that. What we just do, we just pour the mixture into the separating funnel and we allow it to settle. After that, we just tap them up differently. So we will not be needing heat for that. So let's look at crystallization. What does that mean? If you have a dissolved solid, look at it as sugar solution. All right, we have sugar solution. Sugar solution inside this container. All right. Remember that heat can destroy sugar. That is the reason why we use crystallization for sugar solution. But heat cannot easily destroy common salt, and that's why we use evaporation to dryness. Imagine you put salt solution in water, you boil up the water till all the water will go. The highest temperature you're working with is still like 100 degrees Celsius. So now, and the salt can only be even melted, because the part of destruction is it will melt first before you destroy it sometimes. So it will take 801 degrees Celsius for sodium chloride to melt into liquid. So you're just using 100 to boil off. But sugar is not like that. So just quantity of it can turn the sugar to turn brown. Call it caramel. All right, so you will not be able to get your clean sugar if you use the same method. All right, so once it dries up, you find out that the heat will destroy the sugar. All right, so we use crystallization. So that shows that heat is applicable to both crystallization and evaporation to dryness. So this and this will require heat. What about centrifugation? All right, centrifugation is just, we're going to use machine called centrifuge. Why the substances will be placed, let's say blood sample will be placed in the capillary tube, and then the centrifuge will spin. So after spinning, the centrifugal force will act on those substances and will force those substances, insoluble substances, that wouldn't have settled even if you have kept it for 1,000 years. So centrifugation will help you do that. So after that, a centrifuge will be forced down and separation will take place. So we are not applying any heat there too. All right, I hope you got that. What about distillation? What about distillation? Remember, you're going to put this also for question 2. That's how you say question 1, I got it. Question 2, I missed this. Will distillation require heat? Of course, the answer is yes. Why is that? Before you can distill a particular liquid, you have to boil it. You have to get the temperature to boiling point, to the point that the liquid will be converted to vapor. It's the vapor you cool that will call it a distillate using a condenser, all right? So distillation requires the use of heat. So out of all these 7, which of them require this one? 1, this evaporation to dryness, that is 1, crystallization 2, and distillation 3. Let me add, what about if there is sublimation there? Okay, sublimation. Actually, it requires heat, but it's not for, if you are cooling it, it's not going to sublime. Like this guy is already kind of, look at this color of the container and look at this. It can sublime. That is iodine crystals. You can see the purple vapor is already here. But I'm not heating it. That's what you think. The heat at in this particular room, or from my hand, is enough to just warm it up. So, but when you increase heat, you find out that they vaporize more. So, even when you keep a substance and it seems as if you are not heating it, the temperature around can actually help you to sublime some substances. So, and the more heat you apply, the more the rate of sublimation. All right, so that requires it as well. So sublimation, and if you want to separate any substance by sublimation, the first thing you do is to apply heat so that the substance can turn to vapor. Because if you look at it like that, just leave it, they may not sublime at the rate you want it. So this also requires the use of heat. All right, that is question 6 already. How are you doing by testing your knowledge? I want to believe that you learned a lot from the separation techniques videos that you watched, and at the same time you're doing very well. I really want to have the feedback in the comment section. So let's go to question 7. We have this interesting mixtures, and we are just to name. What is the separation technique that you think is appropriate for separating the components of this particular mixture? So I'm going to pick the red pen. So we're going to answer this one after the other. Look at this. Sugar from sugar solution. In fact, I just answered that from previous questions. You put sugar in water, it's from sugar solution. How can you get the sugar out of that solution? The answer is what? Crystallization. All right, so just write it so that you get that crystallization, because the heat can destroy the sugar to form caramel. So we're going to stop the heating, then we'll cool the solution, then sugar will crystallize out. And that's actually how they make sugar in sugar making industries. They plant sugar cane, they squeeze the juice to get molasses, then after that, they crystallize the sugar out. And that's why sugar looks beautiful crystals, like this copper sulfate. Copper sulfate is just blue. All right, you have the sugar to be white. So that is that. So pure water from source solution. Do you know, some of you, and I want you to be truthful, you will have made a mistake by picking another separation technique, because most of you, whenever you see pure water source solution, you just pick evaporation to dryness. But if you have done that, that is wrong. Are you surprised? Evaporation to dryness is when you are interested in the salt from the source solution. So you sacrifice the solvent. But now, you want to get the pure water, the solvent, from source solution. It's possible that we don't even need the source solution. It's the water, the pure water from source solution that we need. All right, maybe some people go somewhere and then someone said, there's no water anywhere. And there is just seawater close. But when you drink it, the salt will cause a lot of things in your system. And you say, oh, you're even hypertensive, you're not supposed to be taking sodium ion and like that. So what do you do? And the chemist say, okay, let me try to get pure water from source solution. That's just what we're saying. And it's basically to boil the water, that vapor, cool it. And whatever you have is not going to taste salt. So you can see the application of the separation techniques now that can save life at any point in time. So you have to understand that. So we're interested in pure water. So the answer is distillation. The reason is we are going to Just like you have your salt solution in brown bottom flask, all right? So this is the salt solution, okay? So then the salt solution, you boil it and the vapor is coming, the salt stays back. So once vapor comes, then you can now pass it through the Libby condenser. So you collect the distillate. Because we're interested in pure water, we're interested in sugar here, all right? So that is why it is distillation. A lot of you will have written evaporation to dryness. Please put it in the comment section. Let's just see whether that is right. Okay, if you want to get iron from sulfur particles, iron is black, sulfur is yellow, but they are mixed in form of mixture. So what do? Because iron can be attracted to a magnet, but sulfur can't. So this gives you magnetic separation. Just bring a magnetic separation. Okay, we'll do that. Just bring a magnet close to this mixture. I can tell you all the iron particles will get attracted to a magnet, leaving behind the non-magnetic particles, which is yellow sulfur particles. So components of crude oil, just like we know, crude oil is a mixture. Some of you maybe are used to calling it petroleum. It's the same thing. Okay, petroleum, crude oil, we mean the same thing. So components, just like we have DPK there, all right, we have AgO, all right. So what is DPK and what is PMS? We also have different substances. So most of the time, maybe you have maybe you drive to a filling station, you just see the price of DPK, AgO, PMS. You'll be wondering like, which one is DPK, which one is that? Okay, so maybe after watching this video, you know, DPK means dual purpose kerosene. Dual like two different uses, dual purpose kerosene. Can use it for aircraft and also for source of heat. So that means kerosene. So when you see DPK in a filling station, we just mean kerosene. So some of them just write it like that because that's the term used in industrial process. So dual purpose kerosene. What about PMS? That is for petrol. That is premium motor spirit. So that's your petrol, all right? So what about AgO? That's your diesel, automated gas oil. Okay. So what we are trying to say is just like we have so many other components of petroleum. We separate petroleum into different components by using what? Each of these liquids, they have their respective boiling point. And that's why we're going to use what we call fractional distillation. As each liquid collects at its own boiling point as different fractions. So we use what we call fractional distillation. And that's what we use in the petroleum industry. And when we're treating this, I showed you the picture of the fractionating column, which is useful in carrying out the effective separation because each of the vapor will travel at different distance and collect at different temperature of their boiling point. So that is very simple. So we use fractional distillation for this. We have done this, we have done this. And let's go to E, which is chlorophyll from green plants. Like I always say, this seems to be the easiest separation technique for most students. But by the time you watch my video of close to 1 hour 30 minutes on just chromatography, you realize that chromatography alone is more complex in uses, operations, and applications more than all other separation techniques combined. All right. So whenever you hear green, blue, just say chromatography. Yeah, you're right. This is chromatography. But like I've told you, chromatography is not just about the color. So watch the video and make sure you understand the full concept of chromatography. How do you separate chlorophyll from green plants? The question is chromatography, but how? All right, so watch the video and see how you can actually bring out and you say this is chlorophyll, rather than the paper chromatography that you know that you just see the spot and you say it has been separated. All right, so the paper chromatography just gives you the idea of the separation. When you want the separation from, how do you collect the extract from plants? How do you now say this particular extract contains so portions of maybe 2 grams of the entire extract of this is chlorophyll. So how much chlorophyll will you get in green plant? Okay, how much plant we have to dry and all that. So go and watch the video and you're going to be able to see a lot of things from there. So we're done with this as well. So let's go to F. Common salt from seawater. All right, so the mistake people made in B, I guess. So you can now see the difference. Whenever you see salt solution, people will just rush evaporation to dryness. No, it depends on what you're interested. Here, we're interested in pure water from salt solution. So, and that's why I said distillation. We're going to distill this liquid. But in this case, common salt is sodium chloride from seawater. Now you need common salt, which is sodium chloride, from the seawater. That's actually what you need now. So how do you separate it? All you need to do is take seawater. Just like I gave an example here, you travel to a particular place, there is no pure water, maybe for fun and all that, no water anyway. And a chemist among you, or someone that has the idea of separation technique, just say, okay, the salt water, I know we can't drink it that way, and because majority of you even have high blood pressure, which you should not take, you should reduce the intake of salt in your food and all that. So now, to just get the pure water from it, just distill the water, cool the vapor, and when you taste that water, there will be no salt in it. Now, you also want to cook now. Maybe you have a particular bush meat and you have done that, you want to prepare it and stuff, and say, oh, there is no salt. Okay, so how do you get common salt from seawater? So you just boil off the water, then you have the pecks of salt that will be left. You can purify it further. You can have sand here too. Do you understand? So like I always say, if it is rock salt now, if you do that, you're going to have sand and salt particles here. So you can't use it that way. Still go ahead and further purify. So the answer for F is common salt from seawater is evaporation to dryness. Okay? Evaporation to dryness. Okay, you evaporate all the liquid to dryness. Like I've told you, it will take about 801 degrees Celsius for salt to melt. So when you boil up the water at 100 or higher, you see have your salt. Common salt is not heat labile, so it can withstand the temperature up to this level before it melts. All right, so let's look at remember, E is chromatography. All right, but I just pointed out it's not just about the color. All right, you need to learn more about chromatography. All right, so the next one is mixture of linseed oil and water. So the point is oil and water. So this linseed, whether it's groundnut oil, whether it's potato, as long as it's oil, they are the esters of all those fatty acids. Okay, so they have those long alkyl chain, all right, that hydrocarbon chain that does not want to relate with water because it doesn't have any polar component or fingers to interact with water. So this linseed is just to distract you because I've seen some students some years that I said this question for, SS1, that is year 10. They just say mixture of linseed oil and water. Then I say, that linseed that Mr. Diamond put there, I think that linseed is not, it has changed something. And the person was just writing story. But remember, oil is oil, whether it's from groundnut oil, whether it's from bean seed, whether it's from anything. All right, so oil is oil. So linseed is just the type of oil. But when we talk about oil, oil is oil in nature. They don't interact with water, so they are immiscible. So don't let us use this to get you confused. So in case you find this in the exam and they say groundnut oil, you are thinking they are talking about something. As long as it's oil, oil does not mix with water. So they are immiscible liquids. And we're going to use separating funnel for that. So the use of separating funnel. Okay, so that is what we're going to do to be able to separate the two. We just pour them in separating funnel. We allow them to settle for some time. After that, you will see distinct layers. Then you tap them off differently, and the separation is done. So let's look at the next one. Blood cells from plasma. Blood cells from plasma. Like I said, when we were treating this, I said when you leave blood cells inside a tube, the highest thing you can clog up. We call it blood clotting. It becomes solid and then no more useful for testing or whatever. So, but you can add something to it that will not allow it to clog. That is EDTA. EDTA is ethylene diamine tetraacetic acid. All right, so ethylene diamine tetraacetic acid. That's what we call EDTA. It's a chelating component. Sometimes when some people get poisoned, they drink EDTA so that to be able to quickly attach all the metal because it has the fingers. Okay, maybe I will draw the structures later for you. So it's just ethylene diamine tetraacetic acid. So it's just like this. Let me see the space where I can do that. Ethylene. So it's like CH2, CH2. Diamine. So N is there, N is there. Okay. So tetraacetic acid. N can form 3 bonds. Can you see that? So this one is now like CH2COOH. Okay, minus plus here. So I'll put the same component here. This one is still CH2. So let me just write it CH2COOH. Can you see? This is CH2COOH. This is also like that. So at this point, a metal can come in, metal can come in, metal can come in, metal can come in. So we call it tetradentate. It's like it has 4 fingers to attract. And most of the poisons are metal. All right? Most of the poisons are metal. So this has a particular hand to bind to metals and you pass it out. So that's the detail. When you put it with blood too, it doesn't get to clog up. So sometimes when you want to analyze blood samples, I'm talking about at the chemistry level, research level, you put this EDTA with it to prevent it from clogging up, and that is EDTA. What I'm saying to make me get that is just blood cells from plasma. So what I was trying to say that made me to remember this is if you put blood inside this, 2 things can happen. The first one is I can clog up. All right, so you will not be able to use it for anything. Even if it doesn't clog up, the solid particles, which are blood cells, like red blood cells, white blood cells, platelets, they will never get settled. They will get suspended within that matrix. So you must use a centrifuge to spin the solid substance down. All right, when you spin it, they will experience a force. They will be forced down and they will get settled. So have this. So, and that's the reason when you take blood in a capillary tube, puncture your finger, put the blood, and then the capillary action will draw the blood up. Then when you put it in centrifuge and it spins, you find out that this place is now red. Those are the blood cells, both white blood cells, red blood cells, platelets, they are there. While you have clear, which is the plasma. So we can use this one to determine what we call your blood packed cell volume, PCV. So when you measure this length, then you can say, oh, this is the length of your blood in this quantity of blood. So we need to know how much blood you have, all right, the level of these red blood cells after spinning. So blood cells from plasma is centrifugation. All right, I want to believe you got that as well. Remember, all these questions, you must attempt them, pause the video, then solve them, and watch the video later and see whether whatever you have written is correct or not. All right, so whatever I say is what is correct. Whatever you have written is objectionable or is debatable. So just understand that these are the answers for all these questions. So let's say iodine crystals from impurities. Iodine crystals from impurity. Iodine crystals from impurity. This is like iodine crystals. Can you see? I don't know whether you can see clearly. This is it. So if I mix it with anything, maybe with this. Okay, let me just take a little quantity from it. Okay. So I bet you will not be able to separate it once you don't know the properties of this mixture, like this. Okay, if I now grind it into powdery, both of them, they are not reacting. Iodine is not reacting with copper sulfate. There is no form of reaction there. So, but you can see that. So if I want my pure copper sulfate back and iodine back, so how will I get it? So the impurity now is copper sulfate. So what we'll do is just, I place something that is cold here and I heat this mixture. You see iodine will just go up here. Just like, look at this container. You can see the colored, this is colored up there. This is the level of iodine crystals and this is colored. It shows that some of it is, they are getting, what is it called? Sublimed. Okay, sublimation is taking place at this own temperature, and that's why some of them are like this. So if this upper part is cold, they will just stick there and become solid back. So the best way to separate this is to heat this mixture, then the iodine will travel up, leaving behind clear copper surface, since there is no form of chemical reaction between them. All right, these two, they don't react. This is just simply mixture. So what method did I just describe? That is what? Sublimation. So that shows that we use sublimation to purify substances that can sublime. Let me test you. How many substances can sublime that you know? I gave about 5 or 6 when we're talking about change of state of matters and all that. So I remember I told you iodine is one, very nice. The ammonium chloride. I told you benzoic acid. All right. I told you about naphthalene. All right. So, and so a host of other solid CO2, which is called dry ice. So those are the substances. I think I mentioned 5 just now that can sublime. So the next one is N-hexane and water. All right. N-hexane and water. So I want to give you the opportunity. Please pause the video now and tell me what separation techniques are you going to use for that when you have N-hexane with water. All right. So the question is, I want to go into the number 8 question, and you tell me this. What is N-hexane? N-hexane is just hexane. N there means normal hexane. All right. So how do you treat N-hexane when it's contact in water? So what separation techniques are you going to use? All right. So it's very simple. It's just like the situation of water and number 8 now, right? The situation of water and kerosene. N-hexane is simply hydrocarbon. It does not have any fingers to form any relationship with water. If it is polar now, then it can interact with water. Look at hexane, it's just like this. 1, 2, 3, 4, 5, 6. Can you see? The next thing is hydrogen. So these bonds are non-polar. Hydrogen, 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 hydrogen. This is an alkane, the 6th member of alkane homologous series. So 6, 6, H2N plus 2. So that makes it H14. 1, 2, 3, 4, 5, 6. 6, 12 plus 2, making 40. So this guy does not have any way to interact with water. Something similar to this, let's say ethanol. Ethanol is C2H5OH. Can you see? Let me show you something. Can you see they look alike? This is ethanol. Once I add O here, let me just put it there so you can see. So this one, when you mix it with water, they are enemies. They will just separate into 2 layers. But if you mix this one with water, what makes the difference? Just this O. They will become a single liquid. Why? It's because this guy can interact with water. Look at even the way it looks. They look like the same family. Why this one looks like another hydrogen? Can you see? So that is ethanol, AlkOH. So ethanol, eth, alcohol. So if water is present, let me say water is this. You know what water will do? They will form hydrogen bond with this guy. Because they are hugging each other through this weak bond, hydrogen bond, so they form together. But this guy has nothing to do with water, and that's the reason why they separate. So any alkane, the higher it is, when you say pentane will not be. After hexane, what's the next thing? heptane, octane, nonane, decane, dodecane, undecane, tridecane, you get to icosane 20. As long as you go, they will not have any finger to move. But immediately you introduce any electronegative element into the structure, they'll be able to interact. Okay, so what I'm saying in essence is that no matter how big the molecule is or small, if it doesn't have any form of interaction with water, so they will not form a single liquid. So ethanol will mix with water, all right? So, but hexane, N-hexane means straight chain, normal hexane, just like the one I drew. So they will not react together, okay? And that is what they will form separating funnel as well, all right? So question 8 now. What does question 8 say? Draw and label diagram separation techniques, kerosene and water. All right. So question 8 is about we have to draw and label diagrams that we use to separate kerosene and water. It's just like this stuff I just explained. Kerosene, when you mix it with water, okay, it's simply hydrocarbon. Okay, mix it with water, they will not form a single liquid. They will separate into layers. Okay, kerosene is lighter than water. That's where density comes in. So we're talking about the miscibility and density here. So what separation technique do we use for that? We use what we call a separating funnel. And I've told you that you have to understand the separating funnel is different from filter funnel. Separating funnel has a tap like this. While the pass is open, we can cover it like that. So we can, let me just use a beaker, okay? Then we'll set it up like this. Can you see that? So we'll clamp it with the third stand. All right, let me tell you where the marks, where some of you will lose the mark when you, what's important is we specify to you that we're separating kerosene and water. So first of all, we want to see the two distinct layers. So can you see that? So you can decide to represent one by cross like this, or even dot, and use a line to represent the second one. Can you see? This shows two distinct layers. Can you see? So that is it. You must be able to distinguish them. That one is another mark entirely. The diagram itself, the way it looks, whether it looks good, may just be one. Okay, if it's correct. Then these two liquids you must distinguish them, that they will form different layers. Can you see? If you use dot dot, you have to be consistent. So when you are separating, when you open this tab, the one that you are collecting, sometimes I can be that detailed, and I usually train my students to that point. This is what I want to see. You can't set up this now. When you say it's dropping, fine. But this is what I want to see. You can't do this and put starter there. I wonder how this one will jump over and put. So I'm that kind of, I pay attention to details to that level. So let's look at this. Which one will be this guy? You must label it. The water will be the denser one, while the kerosene will be the lighter one. So sometimes all these beaker that you think will fetch you mark, sometimes the marking guide or the mark scheme may say, don't award any mark for this. This one that is separating funnel, that is another one that you must separating funnel. So people will label this and say retort stand. They will still get 0. They will label clamp. So that I'm telling you so that you see what is important. If you label clamp now, retort stand, remember beaker, and you know I said the total marks for distance is 5 marks, and you get 0/5, or let's say I just give you 1. You'll be wondering like, how? But let's say I give you just 1 for correct setup, finish. So you just be wondering, I label clamp. That's not the important thing. Even if you label this one standing alone, sometimes you can get all your marks. So, but what is important first, to show the two layers of the two liquids. The one that will stay down and up, that's number 2. Then the apparatus for separation. You know, I've told you that this is separating funnel. It's different from filter funnel. Filter funnel is what you know as funnel. And you see some of you think it's the same thing. So this is a funnel, which is filter funnel. Why this is a separating funnel. So this has a tap. This one does not have. Just we use this one during filtration. All right, we just fold our filter paper here, and pour the mixture, then the filtrate will come out, while the residue will stay on the filter paper. So this one, you turn, once you turn the tap, once you turn it on, then this liquid will continue to flow gently. You don't disturb it. If you disturb it, because they can mix up. All right, I've also seen a situation where I work with one particular, I can't remember the particular solvent now. I was trying to carry out, trying to get different solvent systems for the solubility of different substances like that in the lab. And I found out that there are some two liquids, they didn't mix up, but they have roughly the same density. So they are just dispersed within each other. So it's not this thick, like lighter and denser like this. So that's why density is also another factor in separating funnel. All right. So the lighter one stays up and the heavier one stays down. So remember, whenever you are told, when you are writing WAEC, GC or NECO, and you are told to draw this laboratory setup, remember what is important: the mixture itself, how they separate into two different layers, the name of the apparatus you used. Don't think resource time may or may not fetch you mark, no matter how generous the. If I said the questions, I don't really place so much importance on clamp and resource stand. This is how it will be, but label, you must label the mixture, you must label the apparatus that we're using to carry out the main separation. So those are the most important. So sometimes they give 3 marks. That's what we want to mark. Just say kerosene at the appropriate place, water, and then the name of the apparatus. That's what we want to mark. So everything you do after, you're on your own. So it's important for you to learn what is really important when you are attempting a particular question. How do we obtain pure sodium chloride from rock salt? All right. Like when I was, that's question 9, right? So when I was teaching this particular separation technique, how do you obtain pure NaCl? I was actually like discussing how do we obtain pure NaCl, let's say from rock salt. Before I posed the question, I said, why do you think sodium chloride is very cheap? Do you know if the sodium chloride of this quantity is sold for 50,000, we'll still be buying it? I usually challenge my students, please give me any food that you eat that doesn't contain salt. They start giving me that. I say, okay, may that continue to be your food? And they'll say, no, they want to eat rice, nice stew, nice thing, and everything. Salt, even want to boil yam, you want to do everything. So salt is very important, but it's also very cheap. That shows that God has really helped us in such a way to say, oh, since most of the things you eat will require salt for it to bring out that nice taste. So rock salt must be very cheap. And that's why if you cannot afford anything, rock salt is affordable. The reason is because we have seawater. And if you carry seawater, just pour it on the floor. After the water dries up, you will see the pecks of salt. So we have lots of seawater. And the process to separate it, you don't use anything. Just allow the water to evaporate and the salt. Rock, we also have what we call rock salt. It's just like over the years, just like we have salt in seawater, we also have some of them attached to rock particles, sand particles, and all that. They form rock. And when you look at it, you say, wow, this looks white and it's like salt. By the time you taste it, it's actually salty, so we call it rock salt. So what is inside the rock salt majorly is like the sand particles and salt. And it's like stones like that. Okay, so the first thing you do, how do you obtain pure salt from rock salt? First thing you see is grinding. Okay, you grind the rock into fine powder. You know why? You know the next thing. The next thing is now dissolution. You know, because you have broken the big particles, lump sum, into very fine particles. So that is grinding into. But the solution is now, after you have, let's say this is the lumps of salt, you grind it into powdery form. Okay, then you now add water. So that is the solution. When you add water, you stir it properly. What you are trying to do is just like, you want to dissolve the salt, and the sand particles will just like, hey, here I am, because the salt will dissolve and disappear into the water structure while the salt will be revealed. Then after, what will you carry out? You carry out filtration. Why are we carrying out filtration? Because the impurity is basically sand particles. All right. When you carry out filtration, and this is what it looks like, you fold a filter paper. I taught you how to fold filter paper. If you don't know that, go and watch the video. All right. So you filter this guy, filter it. After you filter, you get clean filtrate, while the sand particles will be trapped on the surface of the filter paper. So you have the filtrate. What do you do with the filtrate? You boil it off, and you have your pure salt. So that is how to get a pure sodium chloride from rock salt. So because is in solid particles, and that's why we have to grind it first. If it were to be liquid, that one is just go straight to this fourth one. So it's actually cheaper, all right, to get salt from seawater than this. But it's very easy. You don't need to go around the water to get the, so just rock salt, you just grind it and you do it. So everything has its own advantage. So, but we are moving from rock salt to sodium chloride. So how do we get pure sodium chloride from rock salt? I've just explained. We use a lot of processes here. In fact, it involves more than one separation technique. Look at the first one is grinding, the second one is dissolution, the third one is filtration, while the third one is evaporation to dryness. And that solves question 8, right? So let's go to question, that solves question 9. The filtration, we use a filter paper, let's say on a beaker. All right, we have it here. Then another one is here. So it's also filtration. Both of them are filtration that I'm talking about. This one, we're having a mixture that is, let's say, this is sugar solution. Okay, that is sugar and water. Then this is water and sand mixture. All right. Let's say filtration is successful in one, but not in the second one. Which of them will have the filtration being successful? All right. So what we're trying to do is, let's assume you want a solution that, a clean water that doesn't taste, you want to taste sugar in it. By the time you filter it, then the filtrate will come here. What will be on this filter paper as residue? Nothing. Nothing will be left here, because sugar is basically soluble. All the particles, the solutes, they are true solution. And through solution, they can pass through the pores of filter paper. So if after filtration, by the time you taste the sugar, you're going to see a sugar taste from there. So you put the sand water system here, you get clear water. All right, but on the filter paper, there will be residue, which is going to be the sand particle. Okay, so you get what we're saying now. So you're going to have residue here. So that means filtration will be successful here, will not be successful. You can't filter out sugar, because sugar is a solute which has dissolved in the water. So and they will come together, they will pass through the pores of filter paper, while the residue, these ones, they are bigger than the pores of the filter paper, and therefore will not follow the filtrate. All right, I hope this is clear. It's very simple. They're just trying to test whether you understand the basic filtration or not. Because some people will say, oh, if you filter salt water, is it going to taste salty? The answer is yes, because that is true solution. They are so small that they pass through the pores of filter paper. Because it's a solution, the blue solution can be can be like CuSO4 solution. All right, this is it. This is copper sulfate. If I add this to water, it will dissolve completely because it's going to form true solution. Remember, despite the fact that it's blue, it's still clear solution. That's the point I always tell you. When we say something is clear, it means like there is no suspended particles. Clear blue solution, all right? Some of you take it as it has to be colorless. Colorless is different, like pure water, colorless. But that colorless solution is also clear because nothing is suspended in it. So a clear solution does not mean it's colorless. It may be blue, may be yellow, and still be clear. So we have clear blue solution as your... So by the time you filter this, the filtrate will still be blue. That's what the question is saying. The filtrate will still be blue because every true solution, the solute is smaller than the pores of the filter paper. And you're going to have it right away. I hope you get that. So it's going to be beautiful that way. So copper sulfate will still be there. So what's the question? Explain why no residue was obtained. Because it's a true solution and the solute particles are smaller than the pores of the filter paper. So they come together with filtrate. And why was the filtrate blue? Because it has passed through that. Copper sulfate is still there in solution. What makes the solution blue is this copper sulfate, and it has gone with the filtrate. Question 12 says, iron filings, common salt, sand particles, and they call it ground mixture. All right, so that means you are not using anything, because don't even think about sieving. Like some of the students say, sieving for what? Everything is mixed they are of the same size. So what will you do? Like I've told you, if you have not watched the videos, I said the first thing you think of whenever you are given a mixture is to look at the constituent of that mixture, then think of the property each of the constituents has, so it will make you to separate it very easy. All right, so like I said, whenever you are given a mixture, all right, the first thing you think about is to check the property of each of the constituents. That will give you an idea of how you will separate them. So let me come close, and you may need to pay attention very well here, okay? So the next question you think about, what property does this one have? What about this? What about this? What about this? All right. So imagine all of them placed into the same container, just like I have this. Okay, just imagine that. I want you to try this. Pause the video at this point and outline. Just tell me how you carry out. I give you this in the lab, and I say I want each of these guys. What will you do? Okay, so the first thing you may want to do is to use magnets. Okay, that one you're not disturbing anything. What it does, just like one of them that can be attracted to magnets, just leave the system. And I think this guy, just bring the magnet, use it to steer it. All the iron filings will just get attracted to magnets, and that is it. We are left with these three. Now we have common salt, we have this. So the next thing, you subject the mixture to heat, okay? So what will happen is, when you are doing that, you just see ammonium chloride will just gently leave as gas. All right, if you need that ammonium chloride, just make sure that where it's going, you have a cold region so that they can easily get, and then they will be cool, and then they will solidify there again. So we'll call it deposition. So that one will separate this. So we have, what is left is now these two, common salt and sand. What will you do? You call the solution. Some of you miss this step, and sometimes the marking guy may be terrible to the point that once you have missed this step, I don't know what you are doing again, and it stops there. Some of you just say evaporation to dryness, or just say sieving. You have lost it. If you don't add the solution, that means you add water. If you don't add this, then you can't go ahead and say you want to carry out evaporation to dryness. All right? So evaporation to dryness will not do anything in the presence of salt, sand, and common salt, which are solid particles. So you carry out dissolution. Okay, when you dissolve, you stir properly. What's the point of stirring? The point of stirring is you want to make sure that the ones that can dissolve, which is common salt, has dissolved completely, all right, in the water. You add enough water. So we have what we have this way. That means inside this water, you just see the sand settled, sand particles, because it is not soluble in water. But this water is the salt solution. Okay? That is the salt solution. So what do you do after doing that? Then you now filter. Why do you have to filter? When you filter this, you will get the filtrate, which is going to be salt solution. Then while the residue will stay on the filter paper in the funnel. So residue will be here, and you have clean salt solution here. Okay. So that is what we're saying. So once you have the residue as sand, so of course you have separated this by magnet, you have separated this by sublimation, all right? Then you have filtered this salt solution, but it's now in liquid, but it's not salt yet. Then you get your sand on the filter paper. So what about the salt solution? What will you do? You now carry out evaporation to dryness. Okay, that means you heat this, subject it to heat, you drive all the water away, then your pecks of salt will be left. Look at this, 1, 2, 3, 4, 5, 6. Some marking guy will put 6. Just imagine you don't talk about stirring properly, you will get 5/6. I'm telling you. But so most time when they say 5, so any 5 of these, but you must, if you don't write this one, at least you'll still get it. If it's part of your discussion, beautiful. But you know that stirring makes all the dissolvable solutes dissolve, all right? By the time you just pour water, you see sand and water will sit together, filter, you get salt part. So what we are saying just, I want you to stir, you add enough water that can dissolve the solutes, then you can have that. All right, so if you got this very well, I would actually love to hear your feedback about this question 12, so I will know if you're really getting this. So you have acquired enough skills for you to get it. So let's go to question 13. All right, question 13. All right, we are certain questions that will cut across the entire separation technique. So if there is anyone that has not been examined and maybe it's your favorite, just wait and let's see how it is. So question 13. Let's see what is there. It's another very interesting question because we have entered into the application form of it. This is not something to cram, something you have to understand. If you don't understand it, most of the questions I'll be solving now, you will not be able to do that. Okay, so it's a chemist attempts to obtain pure water from a sample of colored industrial waste water. All right, the chemist was trying to obtain pure water from a sample of colored industrial wastewater by simple distillation. After the experiment, distillate collected in the receiving flask is also found to be colored. Wow. All right, you already know the separation techniques by distillation. Let me try to draw something simple so that you can see that. Okay, so we have this is where the mixture is. Okay, we may decide to put this so that you can see the sign of heat here. Sometimes you just denote that by the arrow showing the heat. Okay, so at this point you can put the thermometer to represent to measure the temperature around that. Okay, so the vapor, when you are heating, the vapor will pass through this. Let's assume that I've inserted the limbic condenser here. Remember, a tube passes like this inside the Libby condenser. All right, just to manage that. It's not in contact, the vapor here is not in contact with the water that will pump in from here and to be out from here. Like I always tell you, this is never in. Some of you will think it's the same thing. If I put water in here, the water will go down and will come out here. Or I can come here, come up and go here. So most times, if they are flowing out and flowing at the same rate, it will never get filled. But let's say you fill it in here, the water will fill this base and will rise. Can you see that? And will rise and fill this. It's when this gets filled that it comes out. So you have the maximum contact with the coming vapor. Because this is actually, the vapor that is coming here will come here also as vapor. Just like, because the time is very small. So this is the water outside this tube that is cooling it. So maximum contact with this water, not direct contact because it's passing through this tube. So this is water in. We have seen question where they will say you should label Y as water in or water out. It's not anyhow. If you see maybe sometime in your textbook, some of them put it that way. It's not correct. When you go and practice it, you will find out that once you slant it this way, it's better to fill the water. Water flow and flow up like that, not the other way around. If you pump from here, it leaks from here continuously like that. So, but if you pump it from here, it fills up before it comes out. And also take note that this one will be warm, while this is the normal cold water that you are pumping in. The reason is, once this one goes in, it is in contact with the hot vapor and cool it. So the vapor loses energy to this, and that's why it is warm. All right. So the question we are trying to solve is, they distill a colored industrial waste. Distilling is just what I've just put there. Let me just read the question. What does the observation suggest? What is that? They said distillate collected in the receiving flask is also found to be colored. All right. If that is found, if this found to be colored, that means the distillate is not pure. That's what it means. The distillate is meant to be pure. It's meant to be very pure. So, but it's not pure because something happened. So, and that is the first thing, the question they asked. If you are carrying out the distillation of industrial waste and the distillate is also colored like this, so it shows that it's not pure. Okay? Then give two possible explanations for the color distillate. All right. Sometimes when you are heating this, the color component may also vaporize. Maybe it's volatile organics. Okay, I mean volatile organic compound that is present as a volatile color component of this mixture. So once you subject it to heat, both the solvent and the color pigment will vaporize together. It's just like this one hits the boiling point. Let's say the boiling point of the liquid water that I say is 100, and there is another organic component that is like 78 degree or 80 or 90 or something below 100. So both of them are boiling as vapor and they are being collected. That's number one. Number two, there is also what we call priming, the mechanical pushing. When the liquid has a way of the way they behave, just like the way people respond to hard life. Some people will say, don't worry, I'm going to make it, and they keep working hard, while some people will just crumble and they die at that process. Okay, so the liquid mixture also behave differently. So depending on the liquid, so there are some liquid that the way they boil with anger, they can just jump up and they pass. That's mechanical transfer. So they boil through the Libby condenser. There are a lot of substances like that. When we're working with some samples in the lab, there are some group of compounds called saponins. All right, saponins. That is another reason. Saponins are when you see maybe like squeezing plants and you see the liquid it foams and it also tastes bitter. So there are a group of compounds called saponins are present, just like bitter leaves. Okay, so when you boil a situation like this, so they foam. The foaming, the level of the liquid may be here, then the foaming will, and then will pass. So that's the mechanical transfer due to, number one, strong boiling nature of the liquid, and the nature of the component may also cause that priming, mechanical transfer. Also, the volatile organic compounds may be there to transfer some of the compounds there. So you now know that when we are talking about separation techniques, you begin to behave and think like a scientist. So it's not just boiling vapor condense. You can encounter a lot of trouble in the real laboratory sense when just distill something becomes a trouble, except to do some certain things. Okay, so that is, I've answered the questions of the next one. I find out that this one may be a bit difficult for you. All right, so suggest two methods that could be used to obtain a colorless distillate. All right, if you want to suggest methods, just like I said, gentle heating, you don't heat strongly. Sometimes you can place this in a water bath. The vapor from the water bath will be the one to vaporize this. So it's a prolonged heating, but it's gentle heating, so it can vaporize so that the liquid or the mixture will not boil forcefully and transfer mechanically into the distillating, into the other flask that's supposed to collect the distillate. Another one is, sometimes we have a way to introduce what we call anti-bumping. Okay, some of you are hearing this for the first time. Anti-bumping, like sometimes if you have seen distillation set up in the laboratory, even O-level lab, I use it for my students for them to see the difference when you are boiling liquid with or without anti-bumping. Anti-bumping they are just materials like porcelain, just like clay materials. I'm just saying it. They are not reactive. They can't contaminate your liquid the way they are prepared, and they have these pores around them that will be able to allow gas to pass through them gently, so they prevent the forceful bump of the liquid, boiling over. So anti-bumping may be added. Number two, gentle heating of this matrix may be there to make sure that there is no mechanical spilling over of this liquid into that. Then another one, if it is colored, all right, let's say you boil it. All of those methods cannot solve the problem of volatile organics. If you do the gentle boiling, something vaporized because it has to do with temperature will still come over. So what can you do with that? We can use activated charcoal. Activated charcoal also has been prepared, grinding it, putting in concentrated sulfuric acid, then setting it under oven at a particular temperature. Then that one will make charcoal to get activated, all right? And at the end of the day, you will see that they have the ability to adsorb. So we're increasing their adsorptive property. Adsorptive property. Adsorptive property means they have ability to adhere to something on the surface, not real chemistry, just surface chemistry, surface reaction. They get glued to those color materials, and then you can filter off the rest. So it's just a way of, when you boil it with activated charcoal, then you filter off those stuff. You find out that the color is gone, then you can carry out your distillation of whatever matrix that's remaining, and you're going to have a perfect separation like that. So I hope this is also clear. So those are the things that you can do for that. So let's move to the next one quickly so that we can call it a day. So the next question is another very interesting and technical question, which is question 14. Like I've told you, we have entered into application questions, something that will test your brain, test your knowledge, and you'll be wondering like, oh, do I really know these things? So it's not just every time you think the question will come in something that just read and pour. So you must be able to understand it. So the question here, it says that an unknown, okay, the question says an unknown, let's see, an unknown organic solid was known to be either naphthalene. This is funny. an unknown organic naphthalene. Okay. Or what? Or salicylic acid. Okay. Okay, so what is the next one? The solid melted completely when heated in a boiling water bath. Identify the solid and justify your answer. Okay. So the naphthalene melt at 80.2. Okay, 80.2 degrees Celsius. Salicylic acid 159 degrees Celsius. Let's look at naphthalene. Naphthalene is just, there are different substances, okay? Naphthalene is like this. Maybe I should give you, okay. Maybe I should give you this. This is naphthalene. You know benzene ring is 66H6. Okay, so let's just look at this. Benzene ring is 66H6. So this is 1, 2, 3, 4, 5, 6. It's just like this. Okay, so we have continually moving double bond. You will see that all the carbon atoms there, they are equivalent. That means they look the same way. Look at this. This one, double bond and one bond. This one, double bond and one bond. This one, double bond. Every carbon is in touch with something that looks like a double bond and a single bond. So there are like 4 bonds around, 3 bonds around them. So that is remaining 1, 1. So that is why it is 66H6. Can you see? So that is 66H6. That is benzene. When you have the two fused like this, that is naphthalene. All right. So now I want you to draw the structure of this and put it in the comment section. How many carbon? How many hydrogen does this have? That is naphthalene. Okay. Well, salicylic acid is another acid. It's like 2-hydroxybenzoic acid. Look at benzene again. Okay, so I now have benzoic acid. I have COH. Okay, then hydroxy group is there. That reminds me, this salicylic acid, most of you have been seeing it in some cosmetic products. And also, it's another active substance in the preparation of aspirin. When you add substances like acetic anhydride, something like CH3CO, CH3. This is called acetic anhydride because acetic acid, okay, the two, they come together and they eliminate water. CH3COOH, CH3, just like this. CH3COOH. And another CH3, let's say COOH. If you take water from the two, one leave OH, another one H, so you have water left. That is why it is called an hydride. Whatever that is left, this bond journey, you see that it looks like this. So it's the source of this acetylating group. And once that hydrogen burns away, you just see it, the CO will just come like this and CH3. So this is acetyl salicylic acid and this is aspirin. Okay, so we're just looking at a particular student started with naphthalene and salicylic acid. So naphthalene is the melting point is this. Salicylic acid, the melting point is this. Now the student put the, don't forget I said get the molecular formula of this just like I did, and also get the molecular formula of this salicylic acid. Salicylic acid is this guy. That I just show you aspirin structure. So this is salicylic acid. Just acetylate it, get acetyl salicylic acid, and that is aspirin. Okay, so this gets how many carbon we have, how many hydrogen, and how many oxygen. Okay, what is the value for X and Y? What is the value for X, Y, Z? Okay, so I'm putting it in the comment section. Let's see whether you understand how to draw the structure and count the number of carbon and hydrogen and oxygen to make molecular formula or improved formula. Now, The chemistry of the separation technique that they're trying to test here, I want to show you. All right, this is not a main separation technique, but they are testing one part of the property of these guys that we can use it to know which of them. Remember, they said a student was working with two substances, and they told that student that what you are working with can either be this or this, naphthalene or salicylic acid. So, but that student put this substance in a boiling tube and also dip it in a boiling water. It's not that a tube is boiling. A boiling tube is just like a test tube, boiling tube, a test tube, and put it in boiling water. Okay, this water is already boiling. Okay, so boiling water. Okay, so it's boiling. So the question says, and the substance melted. Naphthalene and salicylic acid and the solid melted. So that is what we are talking about. So which of the substance do you think it is? And why? Justify your answer. That's what the question says. Now, naphthalene will be the one to melt. The reason is very simple. If this is boiling water can only boil at this temperature. Normally, pure water boils at 100 degrees C. So this temperature is not enough to melt salicylic acid. But because the melting point of naphthalene is lower, you will see that it will melt this guy. So if the student just sees, oh, this has started melting, it shows that it can never be salicylic acid because the melting point is 159 degrees Celsius. So the one that is lower, whose melting point is lower than the boiling point of water, is actually what the student is working with. So the student is probably working with this, and the reason you will give for justifying the answer is like the boiling water has the maximum temperature of 100 degrees C, as long as another substance is not added. Even if the salt is added, you just tip over to few extra 100. All right. So then you cannot melt salicylic acid. All right, because that melts at 159 degrees Celsius. So that is the main reason that they are actually testing there. The boiling water can only melt a substance whose melting point is lower than the boiling point of water. I hope that is clear. So that is beautiful. So let's look at the question 15. Okay. Question 15 is another technical question which you have to also look at. Okay. The questions. So that student, question 15, they give that student food coloring material. Okay, just like the flavor in food, you have color. Then the next one is what? Methanol. They gave the students methanol as well. What else did they give? Chromatography paper. Chromatography paper. What else? What else? What else? Let's see. A tube, a capillary tube, and a chromatography jar. Okay, so the students carried out the experiment successfully and presented the developed chromatogram to the teacher. Answer the following questions. From the materials provided, identify the stationary phase. Okay. Stationary phase is chromatography paper. Just like I've told you that all forms of chromatography, they have paper chromatography. They have paper as the stationary phase. Then the mobile phase is this is the stationary phase. Okay, so let me just drop this. So then the other question, I think they said, which one is the mobile phase? This is the one that is moving. mobile phase. Okay, then the next question is, which one is a mixture that you want to study? Of course, this is a mixture. Okay, so I think that answers the question. Remember, what is a stationary phase, what's the mobile phase, and what is the mixture? Go back and watch all the videos I made concerning separation techniques, because we're running out of time and we have to quickly complete this. So explain why the baseline origin should be drawn with a pencil line than with ink. All right. So let's say we have the paper chromatography setup like this. You have this baseline, which is called origin. If you draw it with ink, as the solvent is moving up the paper, that is the mobile phase, it's going to separate the ink as well. So it gives false interpretation of your result. So, but if it's pencil, pencil is just like graphite, not dissolving in all the solvent you will use, and also it's not going to react with it. So, and that is why it is drawn with pencil, so that it won't carry out its own separation and to add to the body of the question. So, state the correct relative positions of the mobile phase and the baseline origin. Oh, I've just answered the question in this. The mobile phase is going to be solvent here. Okay? Remember, the relative position, that's what the question says. Relative position of the baseline to the baseline must be above the liquid level. Because if it is the same, so it's going to wash it down. Imagine you put your mixture there and the level of the solvent is there. Instead of to carry, parts will carry up, majority will dissolve in it. So you're not carrying out any separation because you messed up with your mixture. So the relative position is the baseline drawn in pencil should be above the level of your solvent, which is the mobile phase, when you are carrying out the separation techniques using paper chromatography. All right, I hope that is clear. Differentiate between chromatography paper and paper chromatogram. I think I said this at the beginning of the question as well. Chromatography paper is just the stationary phase, just like the paper that you're using. After you have developed it, and what does it mean that you have developed it? You have done this line, you have spotted, you have carried out the separation, and then you have your separated spot. So a paper chromatography that is containing the separated spot is what we call the chromatogram. So paper chromatography is the stationary phase. Why this is the stationary phase, showing the what? Showing the separated component. All right, so that answer that. Now, the student, that's the last question under that E. The student observed two color spots on the chromatogram and concluded that the original mixture contained only two components. The teacher disagreed and said that the mixture could still contain more than two components. Explain why the teacher's position is scientifically correct. And this is a very interesting question. And that is what will show you that you understood chromatography very well. Now, after this separation, okay, the student observed, set up the apparatus very well. There's nothing wrong. Draw the pencil line, spot the picture, and put the. After everything, the student came up with the fact that, oh, this is my paper chromatogram, and my mixture are separated. This is my solvent front. I have two dots here. This is one, this is two. That shows that my mixture contains two components, which could be true. All right, but after taking it to me, I just say, this particular mixture may still contain more than two. And the student was surprised. How? This is one, this is two. What could be the reason for that? Let me just tell you how my position can be scientifically correct. All right, so after carrying out in a particular solvent system, all right, and then this happens. Sometimes there are some colorless substance that is also separated that you can't see. It's just like if I have any form of carbohydrate in the solute, it will separate. They are usually colorless. Some of the amino acids too, they are also very colorless. So they are there. So, but you can't see it. It's because these ones are colored, and that is why. So, number one, you may have to use what we call a locating agent. Okay, so example is ninidrin. Okay, you may not be specific about it, so we'll call them locating agents. Those are the agents that you spray on the paper to form colored products with the spot. For example, if I know that it's a carbohydrate possibly, if I spray this with iodine solution, I will see blue black that will develop from here. It shows that carbohydrate is there. So my locating agent could be that iodine crystal. So different components also form colored spots. I mean, colorless spots may react with locating agent to form colored spots. Apart from that, you are not seeing this because you are just looking at it from your own perspective. When you view this paper, especially if it is TLC you use as this, you can view it under UV light. Okay, when you view it under UV light, you will see some UV sensitive. Especially most of the substances that contain what we call chromophores, they have the conjugated double bonds, so many of it. They are visible under UV light. So you just see that spot, then you mark that plate with pencil, so you can calculate the RF value. So the teacher may be scientifically correct because of the fact that, number one, you've not actually used another solvent system to see if this one spot is actually one spot. Secondly, you have not tried locating agent to see if there are colorless substances that can be revealed by forming color products. Then thirdly, you've not viewed it under UV light, and that is to show you that that particular substance is UV sensitive, and you can see that. So the last question is study the paper chromatography below and carefully answer the following questions. Okay, so this will be projected because the stuff is beautiful here. We have different products. We have A, B, C, and D here. And A is the pure food dye, okay, which is the reference. And B is soft drink, C is candy extract, and D is fruit. Okay, so they're now asking questions from here. You know, because some of you don't know that this kind of question is actually very important. For example, if you have, let's say, a known poison, okay, and you spot it on paper chromatography, name it as P. You now want to see a product. People claim A, B, and C that if they contain this poison, all you need to just set up chromatographic stuff like this, and this is a reference, which is point. After this, you find out that it stays there. All right. So when you spot the product, maybe like drinks, they say it contains it, or tomato paste or something contain this poison. You just need to spot it. After, this one separates like this, 1 and 2. All right. This one separates like this, this, and this one has 3 components. 1, 2, and 3. Let's say like that. Okay. So they can ask you which of them contains this poison. When you look at it, you can see that this C contains this poison. So you can actually ascertain that this C is one that contains the poison. See that analysis? Very simple. Just set it up using paper chromatography and you see. So that is the kind of question that this is testing. And this is the highest form of question you can meet in your exam. But you need to attempt it so that you can understand it. So we have A there, we have 4 components. We have B, we have another 4. We have C, another 4, and D. All of them like that. Okay. So the question says calculate the RF values of any 2 components in the reference sample A. All right, reference sample A is our pure food dye, okay? So, and it asks for products, color blue, red, green, and yellow. So they say you should calculate just RF values of any of the components. Let's pick yellow, for example. Remember what RF value is. That is retention factor. Okay, retention factor. And we calculate by say distance traveled or distance moved. Let me put moved because it's shorter than traveled. Moved by the solute, that is the substance, over distance moved by the solvent. up to the solvent front. Okay, so that is how to calculate RF value. So let's calculate the yellow. If you look at that yellow, trace it is at 1.5. So it travels up to 1.5 and the solvent travels 10. So when you divide this, that is 0.15. It doesn't have unit. This is centimeter, this is centimeter. So it's simply, so 0.15. That's the first one. If you want to make use of the green, so you can calculate the red and tell me the answer in the comment section. But I'm going to be strict to what the question says we should do. So the second one, which is green, this one is for yellow. It's for yellow component of the reference material. So the RF for the green, the next one, is another 3.5. Look at this, the center of the circle, over 10, which is 0.35. All right, that is for green. Calculate the RF values of the red components and put in the comment section. So let's see whether you get it. That's simple. So what's the importance of this RF value? I just showed you I've shown you in the first question, okay? The first thing I treated about poison and all that, so you can see that we use it as a reference. How far does it travel in this solvent? So we have the list of substances, we call it data value. So you can see whether the substance is there by matching the value of the RF value with what we have in the literature, okay? So that is it. So calculate the one for the red and possibly the blue as well. So before we go, so the big question of that say which samples contain one or more components in common with the reference. That means reference which is sample A, B, C, and D. Do they have any substance that is common to them? Okay, common to what is present in A. All right, that means A has so many substances, up to 4, right? Now, any of those 4, is it present in B? Let's find out. Of course, that blue is in B. That means B has something. Let's see whether C also has something. Yes, red is also common to A in C. Let's see D. Okay, that red is also common in this. That shows that, what's the answer? Anything that has B has 1 or 2, C and D. All of this, they have something in common with that substance. And the last question, apart from comparing RF values, suggest one other method that could be used to confirm the identity of a separated component. Can you see that apart from RF values, suggest one other method that can be used to confirm the identity of a separated component? Of course, after the separation, what else can you do? RF value will give you an idea, this is it, okay? You can now, what is that substance that you have separated? You can now carry out different integrated spectroscopic techniques. Like I said, IR can give you the identity, IR will give you the bond. Is there CH in the bond, in the particular sample? Is there CO? All right. Is there C double bond C? So the IR, because this will vibrate. Once the IR passes, they catch the energy and they vibrate. The level of vibration will be interpreted to a number, and then we'll know how this vibrates, so we can actually know that. What about mass spec? Okay, or let's say we have GCMS. Okay, gas chromatography, mass spectroscopy. Okay, so we'll couple them together. So this one will break it into mass to charge, okay, ratio. I'll call it, you can study what we call fragmentation pattern. Fragmentation pattern of the compound. All right, after you have separated it, you now subject it to IR, you find out whether this is there. After that, this one will also give you the molecular mass. Okay, so after that, UV also can help you to know the level of conjugation, how many double bond and conjugation with another. Then we have NMR. All right, these are advanced stuff. So nuclear magnetic resonance. We have this. We have two types of it. We have HNMR, all right, and carbon-13 NMR. This is proton NMR, the carbon-13 NMR. So all this one tells you how many hydrogen, the environment, and stuff like that. By the time you combine all these together, you may come up that this compound is actually aspirin, just like I said. Okay, it's actually aspirin. Okay, like this is acetyl salicylic acid. So because of the fact that after you have done everything, this one shows CH bond is there, CO bond is there and all that. This one tells you the molecular formula. IR will tell you the all these things. The NMR will tell you every fragment. By the time you put everything together, analysis, you can actually identify the substance. And this is how most drugs were discovered, and most of the compounds that are working very well for us now are discovered. Imagine you may have to go to all the plants for you to get just 2 grams of some substances, and people demand they need it. So what you do is synthetic chemistry will now think about how do we synthesize this, how do we form it from simple chemical. So some people can start with benzene, reacting it with COH to form this group, then OH will direct it to this, then we'll call acetylation, and then the aspirin, the drug, is born. And this is how we do a lot of wonderful things in chemistry. You can see that it's been a long day actually, and then just like we started from why do chemists, why are they interested in separation techniques up to this moment, and I want to believe that you have stayed to the end of the video and you learned a lot. So if this is the first video, like I've told you, we started from foundation in chemistry and we are sweeping through all the topics. Let's assume you have a particular topic that is giving you serious headache. When we get there, we're going to break it down just like this. All right, and you find out that actually chemistry is conceptual, like you just need to understand the concept. It's not about cramming. Maybe you thought, chemistry is volatile. Honestly, chemistry is as real as day and night. As you understand all the basic principles, you understand that, oh, chemistry actually forms a story, and by the time you ride with me, you understand all these things. So if you're finding chemistry very difficult, or you want to learn more about so many things in chemistry, make sure you stick to my channel and also share to all your friends who share the same problems with you, maybe challenges of understanding basic concepts, calculation in chemistry and all that. Let's ride together from the foundation to those advanced ones. And I'm telling you, that will be the best decision you can make for yourself as long as your academic journey is concerned. So follow me on all my social media handles at Dr. Jan Knows Chemistry. Bye for now.